Hi, so yeah, this is the 17th video in our exploration of Sylow's theorem. So this is our 17th video in that exploration. So basically what we've been trying to do is to show that actually if you have a group whose order is p to the alpha times m, that implies that there exists a subgroup h of g. Here p and m are being said to be relatively prime. There exists a subgroup h of g such that order of h equals to p to the alpha. Right? That's what we've been working on here. And it's turning out to be a challenge to determine whether this statement is true or not. But we appear to have made some progress. For instance, we seem to have concluded that if g is cyclic, and its order equals to p to the alpha times m, then the result follows. Right? So what really seems to be bothering us now is, well, what if g is not cyclic? Right? What if g is not cyclic? Right? What then? Right? What do we do when g is not cyclic? Can we still conclude that if g is not cyclic and order of g equals to p to the alpha times m, then this implies that we have some subgroup whose order is p to the alpha, right? So we haven't proved this yet, and it appears that if we can prove this last statement here, it appears that we're done. Actually, we'll be able to we'll have guaranteed ourselves a subgroup of order p to the alpha. So we'll have guaranteed ourselves, it appears that we'll have guaranteed ourselves a solution to Sylow's theorem. But still the question remains, well, how do we prove it? How do we prove that if G is not cyclic, there is a subgroup of order p to the alpha, right? So one approach we've been trying to say is that perhaps we can find an element little g of G such that order of little g equals to p to the alpha times L. Right? It seems that if we can show this, we're done as well. But still, the question again remains, how can we show that if a group is not cyclic and its order is p to the alpha times m, then there is an element of the group whose order is p to the alpha times some L, where L is some divisor of m. Okay. So still a lot of mysteries. And before, in the last video, we came upon this idea. Not sure if it will work, but let's at least determine that it won't work. Alright, so the idea goes like this. What we were saying before was, okay, so we have some group, alright, its order is p to the alpha times m. All well and good. Now let's think of the maximum order that an element of G can have. That is for all, how do we define this set? Okay. Let's call it the max of G, alright? We're going to define a set called the max of G, and max of G is going to be equal to the maximum of the set of all order of G such that G is an element of G. Little g is an element of G. Does that make sense? So if we got all the elements of G and took their orders, right, we ask the question, what is the largest order we can possibly get, right? Now, if that order turns out to be p to the alpha times m, okay, right? Did we show before that in that case we're done? Wouldn't that mean that G is cyclic? If G is cyclic, well, can't we conclude that there's a subgroup of order p to the alpha, right? So the cyclic case seems to be the main shut it down. Alright, come on, dude. Alright, just a second. Okay, yeah. The music is off. Yeah, so. Oh man, the music is back. Come on. Alright, the music is off. Better not come on again. All right. So back to our work here. So what we're saying is, look, we're trying to consider the largest possible order an element of G can have, and we're saying, well, if max of G, if max of G actually turns out to be p to the alpha times m, well, wouldn't that mean that, well, we have an element whose order is p to the alpha times m, and wouldn't that mean then that, well, the group is cyclic and thus has some element of some subgroup of order p to the alpha? Okay. So what if the max turns out to be of the form p to the alpha times l? Wouldn't that mean as well that we have some little g whose order equals to p to the alpha times l? Right. And wouldn't this also prove to us that we have a subgroup of order p to the alpha? Because if we have an element of order p to the alpha times l, doesn't that mean that we could think of the cyclic subgroup generated by little g? And if that cyclic subgroup is of the form p to the alpha times l, can't we then conclude that, well, it's cyclic, right? So there must be some subgroup of order p to the alpha. So basically, perhaps this approach, perhaps we could try this approach. We could say this: what if we can show that max of G is always of the form p to the alpha times L, where L is again some divisor of M, and the power of alpha remains the same, right? So if we could do this, wouldn't we be done as well? So let's see if we can establish this. Why would max of G have to be of the form p to the alpha times L? Well, again, it's unclear why. Um, well, what if it's not? What if max of G does not equal to p to the alpha times L? Maybe we can obtain a contradiction. So what? Well, if max of G is not p to the alpha times L, what does that tell us? And does that tell us that max of G then is equal to p to the j times some k, where k is a divisor of L, well, and j is less than alpha? Okay. So what? Suppose the maximum G is p to the j times k. Well, aren't we saying then that there exists some little g in G such that order of little g equals to p to the j times k? Okay. So what? And aren't we saying also then that for all h less than for all h element of the group G, order of h is less than, maybe we should have used a different letter. Okay, well, order of little h is less than or equal to p to the j times k. Right. Is there any reason why this is a contradiction? Why the order of h has to be greater than p to the j times k? Could we come up with something here? Well, again, it's unclear. It's unclear why this should work, or how we would ever find an element whose order is bigger, or why having that all elements are less, the order of all elements is less than or equal to p to the j times k. Why that leads to a contradiction, it's unclear. So, no. So these all seem to be reasons to abandon this approach. It's all well and good that we've defined this set, but it's hard to think, are there any theorems that tell us something about what the largest order has to be, etc. So, yeah, maybe not, maybe not. But yesterday in the shower, the idea came about, maybe we could try the cross products, because we have some group G, and we're saying the order of G is p to the alpha times m. and we're trying to guarantee a subgroup. Oh, maybe not, maybe not. We're trying to guarantee a subgroup H of order P to the alpha. Well, I mean, the idea was if we could find a subgroup of order P, let's say L was a subgroup of G such that order of little l equals to P, right? Perhaps then we could think of L cross L cross L cross L, P times, alpha times, sorry. Right? Because wouldn't the order of L cross L cross L cross L equals to, well, P to the alpha, right? Isn't it the same as the order of L, which is P, the order of the other L, which is P? So the product of all of them, doesn't that give us P to the alpha? Well, does this idea have any merit considering the cross product? Well, I mean, one thing at least we can say for sure is that, well, this thing here, this L cross L, maybe let's write it like this instead, as the product, uh, as alpha runs from, sorry, as, okay, the product as I runs from 1 to alpha of L, and here product is a cross product, right? Well, this is all well and good, but this is this even a subgroup, right? Is it even a subgroup of G, right? It does it have to be? Is L cross L a subgroup of just G, right? It's unclear again, but maybe we could do this instead. That is, okay, suppose we got our group G, all right, and we showed that there is some subgroup K, there is some subgroup K of G, and this subgroup K of G is isomorphic to the thing we came up with before. That is the product, let's say, as I runs from 1 to alpha, I runs from 1 to alpha of L, where L is some subgroup of G, and the order of L equals to alpha, equals to P, sorry. That is, another way of thinking about this is, if we can find some if we can guarantee that there is some subgroup L of G whose order is P, right? Can we then show that the product L cross L cross L alpha times is actually isomorphic to some subgroup of G, right? Because suppose such a K existed, right, such that K is isomorphic to L cross L cross L cross L alpha times, wouldn't that mean that the order of K equals to the order of this product? Let's call this set S, right? This group of products S. If order of K equals to order of S, and order of S is P to the alpha, well, and we're saying then that order of K is also P to the alpha, right? So this is all nice, but again, a lot of question marks. One is, how do we know there's a subgroup whose order is P? That's one question. Next is, even if we're able to find such a subgroup, how do we know that there is going to be some subgroup in G which is going to be isomorphic to L cross L cross L cross L, right? So, I mean, let's think of a best case scenario and see if and see if this approach is worth our while. So, let's do this instead. Let's say, again, we still have some question marks, but let's say that we successfully found some L subgroup of G such that order of L equals to P, okay? And now let's consider the group S, which is L cross L cross L alpha times, otherwise known as the product as I runs from 1 to alpha of L. Okay, this is the product, this kind of product, the cross product, you could say. All right. Well, yeah, okay. So suppose we actually, yeah, we found some L subgroup of G. Well, and we found this group S, right? Isn't S a group? Just isn't the product of a group that is the product of this form X, right? Not just dot, kind of like L cross L cross L cross L, etc. If L is a group, isn't L cross L cross L a group under, well, the operation being done ordered pairwise, like component wise? Okay. If you buy this idea that S is actually a group, it still begs the question, well, how are we going to find some, how do we know that there is some subgroup K of G such that K is isomorphic to this set S, right? So, in particular, can we define an isomorphism? Again, if you're unsure about isomorphisms, please look up the idea. Right? We're going to define, suppose we define an isomorphism phi. Can we define an isomorphism phi from S uh, to some subgroup of K, right? To some subgroup of G, to some K subgroup of G? Right? Can we define an isomorphism? What would it do? Would it take, okay, so if it's an isomorphism, well, what's it going to do? Isn't it going to take uh, elements of S? But what are the elements of S? Aren't they things of the form, let's say, G1, G2, all the way up to G alpha, right? And what are those? What are all of these gonna be equal to in the group K, in the group G? Where are we gonna send these elements to guarantee that phi is an isomorphism, right? Is the question. Of course, once again, and remember before we were saying that P and M are relatively prime. All this information somehow has to be helpful to us. Oh, sorry, up to G sub P. Yeah. Oh, sorry, no, it's G sub alpha. Then we have alpha slots in S. Okay. Well, what's the isomorphism gonna be that takes elements of S to an element of G? Well, I mean, maybe we could set it equal to G sub 1, but yeah, this again is unclear. Um, if we set this equal to G sub 1, is that really gonna give us an isomorphism? Well, what has to be true about an isomorphism? Isn't it supposed to be injective? Well, before we even bother to check whether if it's a homomorphism, just phi of n, if phi of some element of S gives us G sub 1, well, can't we just get another element? Let's say G sub 1 in the first slot, and then the other slots mixed up. Maybe this is G sub alpha, G sub 2, blah, blah, blah. And wouldn't this still also give us G sub 1? So haven't we just got two distinct elements that are giving us G sub 1? Or isn't that possible? So perhaps, because it appears that any permutation of these elements, G sub 1 to G sub alpha, almost any permutation that fixes the first slot appears to will still give us G sub 1. So maybe not, but can we define a legit isomorphism here? because it appears that that's what our task is leading us to. If you can find an isomorphism, uh, well, we appear to be done there. How about phi takes all the elements, let's say G1, G2. For the moment, let's just stick to two elements. Let's assume alpha equals to 2, just to help us do the calculation, because we don't want to be too general if it's not going to work anyway. So, but we don't know yet. Suppose we set phi of G1 times G2 equals to, so here we're saying that the order of G, we're taking it to be p to the 2 times m. P is relatively prime to m, and right, alpha is being taken to equal to 2. Right, clearly. So then L is some subgroup of order P, and our group S is really just L cross L. Oh, okay, let's take that back. Right. Our group S just appears to be L cross L, right, where L has order P. Okay, well, I mean, is this confusing so far? So we just want to work with a special case, maybe that will help us. So we're assuming that the order of G is P squared times some M. P and M are relatively prime indeed, and we're saying that maybe we found some subgroup L of G such that order of L equals to P, okay? All right, we just ran out of time here, so let's take a break and then continue from this exact spot. Yeah, thanks a lot for watching this video.